June 7, 1940, Chrysler headquarters, Highland Park, Michigan. The phone conversation lasted precisely 7 minutes. Yet those few minutes would dramatically alter the course of modern warfare. William Knudsen, President Franklin Roosevelt's newly appointed director of industrial production, asked a question that sounded almost ridiculous on its surface. Can Chrysler build tanks? The man at the other end, K.T. Keller, chief executive of Chrysler Corporation, replied with blunt candor, "I don't know. I've never even seen one." At that point, the U.S. Army possessed only 66 medium tanks. Nazi Germany, meanwhile, had fielded over 3,000 panzers across Europe in barely a year, crushing Poland in 26 days and France in 6 weeks through coordinated armored warfare. America's entire tank force could have been wiped out before lunch on any given day of the Blitzkrieg. The arithmetic of defeat was already being written, in blood across Europe. What neither Knudsen nor Keller realized was that their brief exchange would ignite the most profound industrial revolution in military history. Within 9 months, Chrysler would achieve what government arsenals had never managed. Tanks, those 30-ton steel beasts that once demanded months of meticulous craftsmanship, would soon roll off assembly lines like automobiles, one every 55 minutes at peak output. The experiment would demolish every previous assumption about military manufacturing and prove that American industry could weaponize mass production itself. The challenge began with a basic problem. In mid-1940, the United States ranked 19th in global military strength, just behind Portugal. The Army still had more horses than tanks. The Ordnance Department, charged with weapons development, relied on production techniques unchanged since the First World War. Tanks were hand-built in government arsenals, each one a custom creation, demanding highly skilled artisans. At Rock Island Arsenal in Illinois, only 3 medium tanks could be completed per month at maximum effort, each taking about 12 weeks from raw material to combat readiness. Germany's Panzer output followed similar craft-based methods, but benefited from years of secret rearmament. By 1940, German factories turned out 400 tanks a year, while Britain, despite mechanizing faster than the U.S., managed barely 1,000. Every major power viewed tanks as complex instruments of war requiring master craftsmen, specialized workshops, and months of precise assembly. Keller ended the call and immediately summoned his chief engineer, B.E. Hutchinson, and Frank Zeter, Chrysler's vice president of engineering. Within an hour, they were in his office facing an impossible request. The Army wanted 1,000 medium tanks in under 18 months, along with a new factory and production system, starting from zero experience in tank building. Hutchinson's first question cut straight to the core. What's the current production time for a tank? Zeter had done his homework. Rock Island Arsenal builds 3 M2A1s a month, 12 weeks each, all hand-fitted by expert craftsmen. Hutchinson did the math instantly. At that pace, 1,000 tanks would take 277 years. Keller's reply would define the program. We're not building tanks the Army's way. We're building them our way. If the military wanted 1,000 tanks in 18 months, they would have to accept automotive production methods, which meant Chrysler's engineers needed to see how tanks were being built. Within days, the team visited Rock Island Arsenal. They observed workers hand-fitting armor plates, adjusting track tension by intuition, and machining parts individually to compensate for tolerance gaps. The M2A1 medium tank, 19 tons with a 37mm gun, contained roughly 8,000 separate components, all requiring manual adjustment. No 2 tanks were exactly alike. Keller saw the issue instantly. "This isn't manufacturing, it's sculpture," he said. "You can't scale this up. You can't train new workers fast enough, and you certainly can't make 1,000 tanks this way." Returning to Detroit, the 3 formed what they called the Tank Committee, a small, secretive working group determined to solve the unsolvable. The committee included Owen Skelton, Chrysler's chief production engineer, and experts in tooling, metallurgy, and logistics. From a commandeered conference room at Highland Park, they worked day and night. Their breakthrough came from flipping the central question. Instead of asking how to build tanks faster, they asked how to build tanks differently. Skelton captured the insight perfectly. A car is 2,000 pounds of steel, rubber and glass made from 5,000 parts. We make 3,000 of them a day here. A tank is 30 tons of steel made from 8,000 parts. The only difference is what we're assembling. This new perspective changed everything. If a tank was simply another kind of mechanical product, then automotive mass production principles could apply, though it would require rethinking every element from scratch. Each part had to be redesigned for precision tooling. Every assembly sequence had to be re-engineered for line work. Quality control had to shift from craftsman judgment to measurable standards. The committee discovered that 60% of the M2A1's assembly time was wasted on manual fitting. Hutchinson proposed the radical solution. We manufacture every part to automotive tolerances. Then everything fits without adjustment. Military engineers doubted it could work. Tank parts endured far greater stress than car components, and the precision required would demand new tools, suppliers, and inspection systems. But the potential payoff was enormous. Assembly time could drop from 500 man-hours to as little as 150. Skelton advanced the concept further. If this is car production, we need an assembly line, not a static workstation. By November 1940, they had developed the Chrysler method, a fully industrialized process for tank building. Every major component would be machined to exact tolerances. Armor plates would be standardized and interchangeable. The hull would be welded using production jigs. The turret would mount on a fixed uniform ring, and final assembly would take place on a moving line. When Keller presented the Chrysler method to the Army Ordnance Department, the reception was skeptical, even hostile. Military experts argued that car tolerances were too delicate for combat, that welded armor was weaker than riveted plate, and that producing 10 tanks per day was fantasy. Keller's response was unanswerable. You need 1,000 tanks in 18 months. We can do it. Can anyone else? No one could. By late November 1940, Chrysler received a historic contract. The Army would fund construction of a new purpose-built tank plant. Chrysler would design, equip, and operate it under one condition. The facility had to be designed by Albert Kahn, the Detroit architect who had revolutionized industrial building. Kahn, then 71, was a German Jewish immigrant who had arrived in Detroit at age 11 and learned architecture through apprenticeship. His firm, Albert Kahn Associates, employed 600 architects and engineers and had designed nearly 20% of all U.S. industrial facilities. Kahn's genius lay in treating factories as machines for making machines, structures optimized for light, airflow, and efficiency, with vast column-free spaces ideal for reconfigurable production lines. He pioneered the use of reinforced concrete, which allowed larger open floors and faster construction than traditional steel frame buildings. When Keller approached Kahn about the tank arsenal in early July 1940, he laid out requirements that seemed incompatible. The facility needed to be massive enough to house a complete tank assembly line plus component manufacturing. It needed to be built in months to meet the April deadline. It needed to be bomb-resistant, and it needed to be convertible to civilian production after the war ended. Kahn accepted the commission and threw his entire firm at the problem. Teams worked 18-hour days producing drawings for what would be called the Detroit Arsenal Tank Plant. The main building would measure 1.25 million square feet under one roof, making it one of the largest industrial structures in the world. The design incorporated 3-depth thick concrete walls in critical areas, thick enough to survive bomb hits. The The roof would be reinforced with steel trusses designed to deflect bomb blasts away from windows and ventilation systems. The facility's layout embodied the Chrysler method. A main assembly line would run the length of the building, nearly a 4-mile. Feeder lines would bring major components to the main line at precise intervals. Machine shops would occupy the northern sections, producing drivetrain components and precision parts. Welding bays would fill the southern sections where armor hull sand turrets would be fabricated. The entire design allowed materials to flow in one direction, from raw steel at the west end to finished tanks rolling out the east. Kahn's plans included one innovation that military engineers had never considered. The assembly line would be sunken below floor level, creating a trench approximately 4 ft deep. Tanks would ride on special carriers in this trench, allowing workers to access the underside without jacks or pits. This single design choice would save hundreds of hours per tank by making suspension and drivetrain installation far simpler. On September 9, 1940, groundbreaking occurred on 113 acres of former farmland in Warren Township, Michigan, just north of Detroit. The site had been chosen for its proximity to Chrysler's existing facilities and its access to rail lines. Construction began immediately and proceeded at a pace that seemed reckless. Multiple contractors worked simultaneously, racing to pour foundations, erect walls, and install utilities. Kahn's use of reinforced concrete allowed rapid construction. Each section cured enough to bear load within days. By February 1941, the main building was structurally complete, but far from finished. Walls were up, but windows weren't installed. The roof was complete, but interior systems remained incomplete. Nonetheless, Chrysler began moving equipment into the facility. Machine tools arrived by rail and were installed even as construction continued around them. The most remarkable aspect was the timing. Chrysler had committed to delivering the first tank by April 1941, but the factory wouldn't be complete until May at the earliest. Keller made a decision that would become legendary. We'll build the first tanks inside an unfinished building. This created bizarre working conditions that winter. Michigan's climate in February and Marches brutally cold with temperatures often below freezing. The Detroit arsenal had walls and a roof, but no heating system yet installed, and windows still being fitted. Workers assembled tanks while wearing heavy coats, their breath visible in the frigid air. The solution was improvised but effective. A steam locomotive was brought inside the building, its boiler providing heat to the immediate work area. The image of a steam locomotive inside a factory building belching steam to warm workers assembling tanks captures the sheer determination driving the program. This wasn't careful planning. This was industrial will forcing reality to bend. Meanwhile, the tank committee was solving technical challenges. The drivetrain presented the first major obstacle. The M2A1's transmission was designed for hand assembly. Chrysler engineers redesigned it using automotive principles, creating a unit that could be assembled on a dedicated line and installed as a complete module. Their design reduced assembly time from 40 hours to 4. The suspension system required similar rethinking. Chrysler's engineers standardized every component and created fixtures that allowed pre-assembly and testing before installation. A complete suspension bogie could now be built in 2 hours and bolted to the hull in 20 minutes. The armor hull presented perhaps the greatest challenge. Traditional tank hulls were riveted together from multiple plates, each rivet requiring hand drilling and installation. This process took weeks and created weakness as rivets could shear off under impact, spraying deadly fragments inside the crew compartment. Chrysler proposed all-welded hulls. Thermi objected strenuously. Welded armor had never been combat tested. Welding created heat stress that might compromise armor protection, and welding required skilled operators. Chrysler countered each objection methodically. They produced test welds that proved stronger than riveted joints under ballistic testing. They developed heat treatment processes that eliminated stress concerns. And they demonstrated that semi-skilled workers could produce acceptable welds after just 2 weeks of training using production jigs that positioned every piece perfectly. By March 1941, component production was underway. The tank that would roll out in April would be assembled from parts manufactured in multiple Chrysler facilities and brought to Warren for final assembly. The engine situation required creative problem-solving. The M2A1 used the Continental R975 radial aircraft engine, a reliable power plant that produced 400 horsepower. But Continental couldn't produce engines fast enough. Chrysler needed an alternative. The solution came from engineer Harry Wilson. Chrysler had been developing a new inline six-cylinder engine producing 115 horsepower. Wilson proposed combining 5 of these engines into a single power plant. The concept seemed absurd. Linking 5 separate engines to drive a single output shaft created enormous engineering challenges. But Chrysler engineers loved challenging problems. Under Wilson's direction, they created what would become known as the A57 Multibank engine. The A57 used 5 complete inline-6 engines arranged in a circular pattern around a central gear case. Each engine drove a gear that meshed with a central output gear. The entire assembly produced 425 gross horsepower and 370 net horsepower from 30 cylinders displacing 1,253 in. It was bizarre, complex, and completely unprecedented. It was also brilliant. The multibank engine addressed several problems at once. It utilized existing machinery and parts, enabling immediate manufacturing. It demanded no rare materials or specialized fabrication, and it could be assembled by relatively inexperienced workers following straightforward instructions. The Army disliked it on principle, dismissing it as a Rube Goldberg device, but they couldn't dispute the production schedule. April 12, 1941, one day before Easter Sunday. The Detroit Arsenal tank plant was still incomplete. Sections of the structure had no walls, windows were missing, and the heating system remained unfinished. Yet on the factory floor, the first Chrysler-built M3 medium tank stood completed. The M3 was an advancement of the M2A1, equipped with a larger 75mm gun in a hull sponson and a 37mm cannon in a fully rotating turret. The design was already aging, a compromise between proven methods and urgent necessity. But it became the first tank ever assembled on an automobile-style production line. The official presentation took place 12 days later. On April 24, 1941, the completed M3 rolled out of the still unfinished plant before an audience of military officers, Chrysler executives, local officials, and factory workers. Keller rode inside the tank as it emerged into the spring sunlight. The following demonstration aimed to impress doubtful Army observers. The 28-ton M3 sped across the test ground, crashed through barriers, fired its guns, and showed that mass production had not weakened its combat power. A mock farmhouse was flattened when the tank drove straight through it. But what wasn't visible that day mattered more. Behind that single tank stood a production process unlike anything the military had witnessed. The assembly line was now operational. Component output was increasing. Supplier networks were being organized, and hundreds of workers were learning their roles. By May 1941, production had climbed to 1 tank every other day. In June, 1 tank daily became standard. By July, 2 per day was routine. At the same time, Chrysler was solving the supplier challenge. A single tank required roughly 8,000 parts, and Chrysler couldn't produce everything in-house. B.E. Hutchinson led the supplier effort, traveling through Michigan and neighboring states. His message was straightforward. We need parts built to these specifications, in these quantities, on this schedule. Can you meet it? Many suppliers hesitated, but Hutchinson offered something in return: technical support, advance payments for tooling, and guaranteed contracts. The supplier network grew steadily throughout 1941, eventually including over 400 companies across 32 states. A foundry in Pennsylvania produced final drive housings. Machine shops in Wisconsin made track pins, and a forge in Ohio supplied armor plates. The workforce transformation mirrored the growth of the supply chain. In June 1940, Chrysler had no employees experienced in tank construction. By August 1941, the Detroit arsenal employed 5,800 workers, most learning tank assembly from scratch. Chrysler established training centers where recruits practiced specific operations before moving to the main floor. A worker tasked with installing transmission mounts spent 2 days training on mock setups before touching an actual vehicle, enabling rapid integration with minimal productivity loss. By September 1941, the arsenal was producing 4 tanks daily. The M3 was already proving itself in North Africa, where British units received it under Lend-Lease and dubbed it the Grant, after General Ulysses S. Grant. They praised its reliability, though they criticized its tall profile and sponson-mounted main gun. Meanwhile, Chrysler engineers were developing its successor. From the outset, the Tank Committee had known the M3 was only a transitional model. The sponson-mounted gun restricted traverse and made the vehicle unnecessarily tall. A superior design would feature a fully rotating turret. Working with Army Ordnance engineers, Chrysler created what became the M4 Sherman, the most famous American tank of World War II. Satiru. The M4 used the M3's hull and suspension, but mounted a 75mm gun in a rotating turret. The shift from M3 to M4 showed the adaptability of mass production. Rather than halting operations for retooling, the Detroit arsenal gradually introduced M4 parts, while still completing M3 orders. By February 1942, the line was producing only M4 Shermans. The Sherman was engineered from the beginning for large-scale output. Chrysler's designers influenced every detail to ensure ease of manufacturing. The hull used large cast or welded sections needing little manual fitting. The turret was cast in a single piece at specialized foundries. The drivetrain relied on standardized, interchangeable parts, and even the tracks were optimized for high-speed production. Then came December 7, 1941, the attack on Pearl Harbor, which brought America fully into the war. The measured production ramp-up became a desperate race. The Army's tank demands skyrocketed overnight. The 1,000 tanks that once seemed ambitious now looked woefully insufficient. Chrysler reacted by intensifying production. The plant that had produced 4 tanks per day in September 1941 was turning out 12 by March 1942 and 18 by July. This surge required constant problem-solving. Bottlenecks arose as various processes failed to keep up. A shortage of welders delayed hull fabrication until Chrysler created welding schools producing 50 graduates per week. Machine tool scarcity hampered part production until priority shipments were arranged. Owen Skelton, promoted to general manufacturing manager, implemented a system called production expediting. Teams of engineers tracked every process, pinpointing delays within hours and resolving them within days. The culture at the Detroit arsenal became obsessed with performance metrics. Daily output numbers were posted publicly. Workers knew precisely how many tanks had been completed that day, that week, that month. Competition between shifts became fierce, each striving to outproduce the others. By December 1942, the Detroit arsenal achieved what experts had declared impossible. In a single month, 896 Sherman tanks rolled off the line, 29 per day, a rate surpassing all other U.S. tank factories combined. The Detroit arsenal alone was now outproducing the entire German tank industry. This accomplishment resulted from unrelenting refinement. The assembly line now operated with machine-like precision. Tanks moved from station to station every 55 minutes. Workers had refined their operations through months of repetition. Suppliers delivered components with such reliability that inventory could be minimized. Quality control had evolved into a science with inspectors checking dimensions and fit at every stage. The IU-896 tank month represented the peak of wartime production. Efficiency. While later months saw sustained high production, December 1942 remained the single-month record for the duration of the war. It demonstrated that tank production had been transformed from craft to industry. The Detroit Arsenal's success created demands for its replication. The Army wanted more tank production capacity distributed geographically. Several additional tank plants were constructed, including facilities operated by General Motors, Pressed Steel Car Company, and Pacific Car and Foundry. Each plant adopted the assembly line approach and precision manufacturing methods, but the Detroit Arsenal remained unique in its production volume and efficiency. By war's end in August 1945, the facility had produced 22,134 tanks of various models. This represented approximately 25% of all tanks built in the United States during World War II. The tanks themselves evolved continuously. The Sherman went through multiple variants, each incorporating improvements. The M4A1 featured a cast hull. The M4A2 used twin diesel engines for improved fuel efficiency in British and Soviet service. The M4A3 mounted the Ford GAV-8 engine. The M4A4 used the Chrysler A57 Multibank engine. Each variant required production line modifications, yet the basic assembly process remained constant. This flexibility was another advantage. Craftsman production required rebuilding skills for each design change. Assembly line production simply required modifying fixtures and updating work instructions. The Sherman's reputation has been debated endlessly. It was inferior to German tanks like the Tiger and Panther in armor protection and gunpowder. Sherman crews faced terrifying odds in direct combat with these heavier vehicles. But the Sherman had advantages that mattered more in the aggregate. It was reliable, maintaining operational readiness far better than German tanks. It was easy to repair with standardized components and well-trained maintenance crews. And above all, it was available in overwhelming numbers. The production mathematics told the strategic story. Germany produced approximately 24,000 main battle tanks from 1939 to 1945. The Soviet Union built approximately 105,000 tanks in the same period. Britain managed about 28,000. The United States, entering large-scale production in 1942, built approximately 88,000 to 90,000 tanks by 1945. The Detroit Arsenal alone produced roughly 1/4 of American output. But numbers tell only part of the story. The real transformation was in how tanks were produced. Before 1940, every major power treated tank manufacturing as specialized military work, requiring years of experience and government arsenals. After Detroit Arsenal, tank production was understood as industrial work requiring engineering skill and production expertise. This philosophical shift had profound implications. It meant production could be scaled rapidly by engaging private industry. It meant workers could be trained in weeks rather than years. It meant supply chains could be distributed across entire continents. And it meant production capacity could be maintained even as experienced workers entered military service. After World War II ended, Chrysler continued operating the Detroit Arsenal under government contract. Tank production ceased temporarily, but resumed with the Korean War. From 1952 to 1954, the facility produced 3,447 patent tanks. During the 1960s, it manufactured M60 tanks. In 1979, it began producing components for the M1 Abrams. In 1982, facing financial pressure, Chrysler sold its defense division to General Dynamics for $336.1 million. General Dynamics continued tank production at the Arsenal until 1996, when consolidation shifted operations to the Lemur Army Tank Plant in Ohio. The Detroit Arsenal site today hosts the United States Army TCOM Life Cycle Management Command and the Combat Capabilities Development Command Ground Vehicle Systems Center. A Michigan historical marker commemorates the site's role, noting that it produced more than 22,000 tanks and proved that American industrial might could be weaponized. The story's key figures went on to varying fates. Kaufman Thumela continued leading Chrysler through the war years, becoming chairman in 1950. He retired in 1956. Albert Kahn died on December 8, 1942, just months after the Detroit arsenal reached peak production. His architectural innovations influenced industrial construction throughout the 20th century. William Knudsen served throughout the war as Lieutenant General in the United States Army. Commissioned January 28, 1942, the highest rank ever given to someone not already in military service. He died in 1948. The Sherman tanks built at Detroit Arsenal served in every theater of World War II. They landed on Normandy beaches on D-Day. They fought across France and Germany. They island-hopped through the Pacific with Marine Corps units. They served in British, Canadian, Free, Soviet, and Chinese armies under Lend-Lease. Many Shermans survived the war and continued in service for decades. Israel used modified Shermans in the 1967 Six-Day War and the 1973 Yom Kippur War. South American nations operated Shermans into the 1980s. A few remain in running condition today, preserved as monuments to an era when industrial capacity determined military power. The transformation of tank manufacturing from craft to industry happened because a handful of engineers and industrialists refused to accept conventional wisdom. They saw no fundamental difference between assembling an automobile and assembling a tank. Both were mechanical devices built from thousands of components. Both could be manufactured on moving assembly lines by specialized workers performing specific operations. This insight, simple in retrospect, was revolutionary in 1940. It required looking past surface differences to see underlying similarities. It required engineering courage to redesign military equipment despite military resistance. And it required industrial confidence to commit to production methods that had never been attempted at such scale. The success of the Detroit arsenal validated Henry Ford's earlier insights about mass production while extending them into new domains. Ford had proved that interchangeable parts and moving assembly lines could produce automobiles at unprecedented volume and low cost. Chrysler proved these methods could produce instruments of war with equal efficiency. This possibility transformed World War II's outcome. Without mass-reduced tanks, American ground forces would have fought at severe numerical disadvantage. Britain would have struggled to replace losses. The Soviet Union benefited from thousands of American-made Shermans. The ability to produce 88,000 to 90,000 tanks in 4 years was unique to American industrial capacity, and roughly a quarter came from a single facility in Warren, Michigan. The invisible achievement was perhaps greater than the visible one. The Detroit arsenal didn't just build tanks. It proved a concept. It demonstrated that private industry could solve government problems faster and more efficiently than government could solve them itself. It showed that engineering expertise mattered more than military tradition. It validated the idea that American industrial capacity, if properly mobilized, represented a war-winning advantage. This validation shaped post-war American strategy. The concept of maintaining industrial capacity that could be rapidly converted to military production became central to Cold War planning. The idea that American industry could outproduce any potential adversary became doctrine, and the relationship between private contractors and military procurement that began with the Detroit arsenal contract became permanent structure. The engineers who made the Detroit arsenal possible were practicing systems thinking before the term existed. They didn't just solve individual problems. They designed an entire system where components, suppliers, workers, assembly processes, and quality control functioned as integrated whole. Each element was optimized not in isolation but as part of the larger production system. This systems approach was visible in countless details. The assembly line's sunken trench eliminated a bottleneck in undercarriage assembly. The supplier network created resilience by distributing production across geography and multiple companies. The training system created a pipeline of skilled labor that could replace losses and support expansion. Every element was designed to scale. When production needed to double, the system could absorb that increase by adding shifts, expanding supplier orders, and training more workers. When new tank variants were introduced, the system could adapt by modifying fixtures and updating procedures. The ultimate measure of success was efficiency improvement over time. The heat. First M3 tank, built in April 1941, required approximately 500 man-hours of labor. By December 1942, M4 Shermans were being built in approximately 150 man-hours. This productivity improvement of more than 300% came from continuous optimization. Every month, engineers studied production data, identifying operations taking too long or producing defects. They analyzed why workers struggled with particular tasks and redesigned fixtures or procedures. They questioned every decision, asking whether there was a faster, simpler, better way. This culture of continuous improvement, borrowed from civilian automotive production, was alien to military arsenals accustomed to unchanging procedures, but it was essential to achieving the production volumes that the war demanded. The financial cost was substantial, but modest compared to output. The facility's initial construction cost approximately $20 million. Equipment and tooling added another $30 million. By war's end, total investment exceeded $100 million. But the 234 tanks produced represented a value exceeding $2 billion. The return on investment was enormous by any measure. More significant than financial return was strategic value. The Detroit Arsenal's production capacity allowed American ground forces to fight with numerical superiority in armored vehicles. This advantage was crucial in campaigns from North Africa to Germany. Without the production capacity created at Detroit Arsenal and similar facilities, World War II's outcome might have been very different. The story of the Detroit Arsenal is ultimately about seeing possibilities others missed. When Keller told Knudsen he had never seen one of these things, he was acknowledging ignorance, but not inability. Chrysler's engineers didn't know how to build tanks, but they knew how to build complicated mechanical assemblies from thousands of components. This confidence that engineering could solve any production problem was characteristically American. European manufacturers accepted that tanks were inherently different from civilian products, requiring specialized facilities and craftsman skills. American industrialists saw only machines, all of which could be broken down into components, processes, and assembly sequences. The Detroit Arsenal validated this philosophy completely. In 9 months, Chrysler went from zero tank production to delivering finished vehicles. In 18 months, they were producing tanks at rates that exceeded requirements. In 3 years, they had delivered more tanks than most nations produced in the entire war. The engineers and workers who made this achievement possible were ordinary people doing extraordinary work. They weren't heroes in the conventional sense. They didn't storm beaches or liberate concentration camps, but they built the tools that made those achievements possible. This democratization of military production was itself revolutionary. In previous wars, weapons came from specialized arsenals operated by master craftsmen. Production was limited by the availability of skilled labor. In World War II, American weapons came from automobile factories and dozens of civilian industries that converted to military production. The workers were housewives, recent high school graduates, farmers, and shop clerks who learned specific operations and performed them repeatedly. The Detroit Arsenal was the symbol and proof of this transformation. It showed that private industry could build military equipment more efficiently than government arsenals. It demonstrated that production methods developed for civilian goods could apply to weapons of war. It validated the arsenal of democracy concept, and it established that in modern warfare industrial capacity was as important as military strategy. Today, Most people driving past the site have no idea what happened there, but the legacy persists in less visible ways. The M1 Abrams tank is built using production methods descended directly from those developed at Detroit Arsenal. Modern military manufacturing relies on private contractors using industrial production techniques. The integration of supplier networks, precision manufacturing, and assembly line production that Chrysler pioneered remains standard practice. The transformation from craft to industry that began on those 113 acres in Warren, Michigan, fundamentally changed how nations equip their militaries. It proved that engineering expertise could solve seemingly impossible problems by refusing to accept conventional limitations. It showed that production principles could apply to the most complex military equipment. And it demonstrated that American industrial capacity, when properly mobilized, could produce the tools of victory in quantities that overwhelmed any adversary. This was the invisible weapon that helped win World War II. Not superior technology or better tactics or more resources, though all those mattered. The decisive advantage was the ability to treat war as an industrial problem and solve it with industrial methods. Kaufman Thummer Keller, answering that telephone call on June 7, 1940, couldn't have imagined where his honest admission would lead. But in saying he didn't know but would figure it out, he articulated the confidence that made victory possible. The engineers who designed the production system, the workers who operated it, and the suppliers who fed it were all engaged in a collective achievement that changed warfare itself. They proved that tanks could roll off assembly lines like cars. They showed that complexity was no barrier to mass production, and they demonstrated that American industrial genius, when challenged, could accomplish what military traditions said was impossible. The story deserves remembrance not only for what was created, but for how creation itself was transformed. The Detroit Arsenal was more than just a tank plant. It stood as proof that engineering imagination could overcome any obstacle when the right people posed the right questions and refused to believe that impossible meant anything more than not yet attempted. Tanks are mostly gone now, scrapped or resting in museums. The factory has been largely torn down, and the workers are long gone, but the method endures. The realization that complex mechanical systems can be mass-produced regardless of purpose survives in every modern manufacturing line. And the confidence that engineering can overcome production barriers lives on in every industrial designer who looks at a challenging product and asks, not can we build it, but how can we build it efficiently, reliably, and at scale? That question, asked and answered at the Detroit Arsenal between 1940 and 1945, changed the course of history. It made mass-produced warfare a reality. It confirmed American industrial methods as superior to European craftsmanship traditions. It demonstrated that private industry could outperform government arsenals. And it revealed that when engineers face impossible problems, they sometimes solve them simply by refusing to accept impossibility. This is why the story matters. Not because tanks are fascinating, though they are. Not because World War II is significant, though it was, but because the Detroit Arsenal embodies a mindset about problem-solving that remains powerful even today. See the underlying patterns, not just the visible differences. Apply proven techniques to new challenges. Design systems, not just parts. And never assume something cannot be done merely because it hasn't been done before. In 9 months, Chrysler went from never having seen a tank to producing them on assembly lines. In 18 months, they surpassed every expectation. In 4 years, they built more tanks than most nations produced during the entire war. This achievement was possible because engineers looked at a military dilemma and saw an industrial opportunity. They refused to be limited by tradition, convention, or doubt. They solved the problem, and that remains their greatest legacy. Not the tanks themselves, but the proof they offered, that engineering confidence, industrial strength, and systematic thinking can accomplish what appears unattainable. When someone insists it can't be done, the right response is often, Show me why not, and let's find a way. That attitude, applied with conviction and creativity, built an arsenal that helped preserve democracy.